Hello everyone, and welcome to today's lecture on Introduction to Digital Logic, Boolean Algebra, and Karnaugh Maps by Powell. As always, I'm using the Digital Design Principles and Practices by John F. Wakerly as a reference. So what is Boolean Algebra? It was named after George Boole. It is a branch of algebra where variables are either true or false, 1 or 0. It's a mathematical foundation for digital circuits and modern computing. Why is it important? Digital circuit design. It's essential for building and understanding logic gates. Simplification. Reduces complex expressions for efficient circuits. And this allows a systematic approach to logical relationships. So basic concepts. Variables and literals. Boolean variables can only be one of two values, 0 or 1, also called binary variables or logic levels. Literals, a variable or its complement, example a or a prime or a bar. Boolean operators and. So this will be a bit of a review from my last video. So the and operator, it's a symbol dot or implied, either a dot b or just ab. Its output is 1 or true only if all inputs are 1, otherwise 0. Example, y a and b, or y is equal to a dot b. And here you can see the truth table. Boolean operators for or operator, symbol plus, rule, output is 1 or true if any input is 1. Output is 0 only if all inputs are 0. Y equals a or b, or y equals a plus b. And here's the truth table. Boolean operations not, a not operator or inversion. The symbol is prime or over bar. Inverts the input. 1 becomes 0 and 0 becomes 1. Example, y is equal to not a, or y is equal to a prime, or y is equal to a bar. And here is the truth table. Boolean algebra, commutative and associative laws. Boolean algebra and theorems are fundamental rules for manipulating Boolean expressions. The commutative laws. Order does not matter. For example, a or b is equal to b or a, and a and b is equal to b and a. Associative laws. Grouping doesn't matter for the same operator. So for a or b, bracket a, c, or c is equal to a or bracket b or c, bracket. Another one, bracket a and b, bracket and c equals a, bracket b and c, bracket. Distributive identity and complement. The distributive laws. So a and b or c is equal to a and b or a and c. And then a or b and c is equal to a or b and a or c. It's only unique to Boolean algebra. The identity laws. A or 0 is equal to a. Adding false doesn't change value. A and 1 is equal to a. Ending with true doesn't change value. Complement laws. A or a prime is equal to 1. A or not a is always true. Important theorems. Idempotent, null, and absorption. So, idempotent, a or a is equal to a, and is equal to a. Null laws. A or 1 is equal to 1, and a and 0 is equal to 0. Absorption. A or a and b is equal to a and a or b is equal to a. De Morgan's theorems. De Morgan's theorems are powerful for simplifying expressions with complements. Convert between sum of products and product of sums forms. The first theorem, a or b prime is equal to a prime and b prime. The complement of a sum or is the product and of individual complements. Not apple or banana is equivalent to not apple and not banana. Second theorem, a and b prime is equal to a prime or b prime. It's the complement of a product and is the sum or of individual complements. And then finally, the double negation involution law. A prime prime is equal to a. And here you can see a table that summarizes all the Boolean algebra theorems. And the table gives it in the or form, or sum of products form, or the and form, product of sums. So let's look at some basic simplification examples. Example 1, simplify y equal to a or a and b, or a and b and c, or a and b and c prime. Factor out the common terms. So we get y is equal to a and b and 1, or c prime. Apply the identity law. So we get y is equal to a and b and 1. And apply another identity law, we get y is equal to a and b. Simplify f is equal to a or a prime and b. So we first apply the distributive law to get f equal to a or a prime and a or b. Applying the complement law, we get f is equal to 1 and a or b. And we finally get f is equal to a and a or b. Some more examples. Simplify g is equal to bracket a or b and bracket a or b prime. So by applying the distributive law in reverse, we get g is equal to a or bracket b and b prime bracket. And applying the complement law, we get g is equal to a or 0. With the identity law, we get g is equal to a. To simplify, h is equal to a and b, or a and b prime, or a prime and b. We factor out a from the first two terms, which gives us h is equal to a and bracket b or b prime, bracket, or a prime and b. Applying the complement law, we get h is equal to a and 1, or a prime and b. Applying the identity law, we get h is equal to a or a prime and b. Applying the distributive law, we get h is equal to a or a prime and bracket a or b. Applying the complement law, we get 1 and bracket a or b. And finally, with the identity law, we get h is equal to a or b. Now we talk about the Karnaugh maps, which makes simplification of Boolean algebra expressions easier. It was developed by Maurice Karnaugh in 1953, and they provide a systemic or visual way to reduce complex logic circuits to their simplest form, making them easier and more cost-effective to implement. While Boolean algebra laws and theorems can be used to simplify expressions, they can be cumbersome and prone to errors, especially for expressions with many variables. K-maps offer several advantages. It offers a visual aid to provide a clear representation of a Boolean function. Its systemic approach offers a step-by-step method reducing the chances of missing simplification opportunities. It offers guaranteed minimization and also handles do-not-care conditions. So creating a K-map. A Boolean function is plotted on a grid, the K-map. Adjacent cells in the map differ by only one variable. Group of ones midterms are formed to identify common terms. The largest possible group of ones in powers of 2, example 1, 2, 4, and 8, are circled. Each group represents a simplified product term. So a three variable K-map example for the function ABC, which is the sum of 0, 2, 4, with which means it's 1 for 0, 2, 4, 5, and 6. So we can see the truth table over here, where it's true for the midterms of 0, 2, 4, 5, and 6. So we construct our K-map, A over here and BC over here, with the corresponding midterms for M0 and M2, M4, M5, and M6. So group 1, cells M0, 2, 4, and 6, so these cells. This group covers C prime. Notice how B changes, A changes, but C is always 0. Cells M4 and M5. This group covers AB prime. Notice C changes, but A is 1 and B is 0. Therefore, F equals C prime or AB prime. Another K-map example. F equals ABC, where it's 1 for 0 for the midterm 0, 2, 4, and 6. You can see the truth table over here. So with the Karnaugh map is constructed as follows. We get the midterms 0, 2, 4, and 6 being 1 here. So we group it as a group of 4 ones. So this one and this one. which covers C prime. Therefore, the simplification is f is equal to C prime. So in the next video, I'm going to probably talk about more advanced combinational logic, such as decoders, encoders, and multiplexers. Thank you, like, and subscribe.